Okay, so this is number 4 in the series of videos for artificial intelligence. In the last video, the main take-home message is that we can come up with a search algorithm called A* search, and it uses a heuristic to measure the distance from any state that we can get to the nearest optimal goal. And it uses that in conjunction with the path cost at any particular state to give us an f-cost, which is the sum of the path cost and the heuristic. And by using that to order the way in which we explore states within the search problem, we can get something that is optimal and complete. And if the heuristic is good, if it's been well designed, if it's accurate, then the chances are that this is going to be much more efficient than an uninformed search like straight breadth first, depth first, or iterative deepening. The downside is that A* search, as we've seen it so far, still requires potentially an exponential quantity of memory, in addition to being an exponential time problem, and it's the memory that will often cause us a problem first. So what we want to look at now is how it might be possible to take A* and improve it so that it doesn't require catastrophic amounts of memory in order to work. Now, the iterative deepening A* algorithm takes a very straightforward approach to this. You may be able to guess how this works. We've already seen iterative deepening used in such a way that at each iteration it searches to a greater depth than it did at the previous one, typically expanding the depth out by 1 at each step, at each iteration. The possibility that we want to look at now isn't doing iterative deepening search in the sense of increasing the length of the path. Okay? We would previously have been increasing the length of the path by 1 at each iteration. What we want to try now is searching within some particular limit on the f-cost. And if we fail when we search within that particular limit, we then search to a deeper f-cost. And we keep doing that until we find a goal or establish that we can't find any solution. Now, the trick that lets us do this is fairly simple. If we search within a particular f-cost, at some point we're going to cut the search off because we've got to a state that has an f-cost that's beyond our limit. We just keep track throughout the search of the smallest f-cost that we've ever seen that's beyond the limit we're searching within. And the smallest value of that f-cost is used at the next iteration to search a little bit further. Now, I'm going to explain this using pseudocode again, and also after the pseudocode using just a little specific example, because I think that might be a little clearer. The pseudocode is straightforward. We have this function called contour, which is recursive. Now, I'll explain to you what this function actually does before I try and go through it in detail, because anyone of you who's had supervisions with me on the subject of programming in ML will be familiar with the fact that I'm a firm believer that in trying to understand a recursive function, you should not try and unwind a whole stack of recursive calls in your head, because that will just get you confused. The way that you do this is to assume that your function already works, and to analyze it on that basis, because the function must work, or it wouldn't work, eh? What insights I give you. The function contour takes a state, the current f-limit that you're searching within, and the path that you constructed so far to get to the state. What it returns will either be an empty list indicating that you've gone beyond the current f-limit, and also a new f-limit that is the smallest thing that you've seen beyond the current f limit. Alternatively, if S is a goal, it can return a path to S, and that solution is the solution that you're looking for. So those are the two things that it can possibly return. So just looking at this line by line, we first set a variable called nextf to be infinity. Now this is going to be used to keep track of the smallest f cost that we see beyond our current limit, f limit. The first if here just says that if the state we've got to has an f cost that's beyond the limit we're searching in, then we return an empty path to indicate that we've cut the search off, and we return the value, the f cost of the current state. Okay, now that f of s in the first if statement is the value that we've seen when we've gone beyond the current f limit. The second if statement just says if s is a goal, then we're done, so we can return s const onto the existing path, which is going to be our solution. And then here I'm returning the f limit, but it doesn't really matter what you return here, because you found a solution. Okay, so that's essentially just a placeholder. The for is taking each state that you can get from by applying an action in S. Okay, so each S prime that you can get to from S. And in each case, it's trying to continue the search from S prime. So it calls contour again, this time on S prime. We're still searching within the same f limit, and now we've added S to the path that we're constructing. Now what we can get back from that is either an empty list with an f cost that we've seen beyond the current f limit, or a goal. Now if we found a goal in one of these recursive calls to contour, then we're done. Okay, so if the new path is non-empty, we must have found a goal, so we just pass it back up the succession of recursive calls, and everything finishes. Otherwise, nextf is being used to keep the smallest f that we've seen beyond the current f limit. Okay, so within the for, we have this if that sees whether the new path that's come back is non-empty. Okay, and the last line happens if the new path that's come back is empty, which means that in the recursive call to contour, we inevitably went beyond the current f limit that we're searching in. The new f that gets passed back from that is the smallest f cost that we saw beyond the current f limit. So we just make nextf be the smaller of its current value and the new f that was passed back. So because that's happening within this for loop that calls contour recursively on each s prime that we can possibly get to, nextf here ends up being the smallest f cost that we see beyond the f limit anywhere in a search that happens under the state S, which contour was originally called with. The only thing left is to get this thing started in the first place. So this is iterative deepening A star. The f limit that we start with is just the f cost of our start state, and then the rest of it is easy. We keep going until either we find a solution or we establish that there isn't one. We call contour on the start state with the existing f limit and an empty path. That comes back with a new path and a new f limit. So f limit here is updated by the result that comes back from contour. If the path that we got back is non-empty, we must have found a solution, so we return it. If the f limit that comes back is infinite, there can't be a solution, so we're done. And we go around the while loop again. But because f limit is updated when we call contour and get the result back, after the first call to contour, f limit is updated to be the smallest f cost that we saw beyond the initial f limit. So every time this while loop clicks around, the f limit gets updated to be the next biggest limit that we want to search in. So here is an example in hopefully a more amenable and pictorial form. We start here by calling contour on the root node with an f cost of 3. That then calls contour recursively for each of the children of the root node, and each of those has an f cost that is beyond the current f limit. But what contour then passes back is the smallest of those. So contour comes back with an empty path and a new f cost of 4. And it now goes around again. So now it calls contour on the root node with an f limit of 4. Over on the left, it immediately sees a 7. So within the while loop in contour, if we look back here, next f is updated to 7. It then calls contour on the second child of the root node. It sees that if its f cost is 4, so we're still within the f limit, it expands out the 3 children, which have f costs of 5, 9 and 10, which are all beyond the limit. So we get a value of 5 back. That's then less than 7. So within contour, again back here, next f has been updated to have a value of 5. And then we call on the right hand side and we immediately see a value of f which is 5, which is beyond the existing limit of 4. And so we cut off, and the next f cost that we want to search within that gets passed back to the root again is 5, which is the smallest value we've seen anywhere in the tree that's beyond the first limit on the f cost of 4. Now we go through again. So we start from the root. On the left we see 7, which is greater than 5, so we stop. And we keep our value next f as 7 until we see something smaller. We look in the middle of the tree, we see an f cost of 4, that's within our limit. We go down to the first subtree in the middle of the diagram, we see an f cost of 5, which is still okay because our limit is 5. We expand this, we see children with costs 8, 12 and 7. All of these are beyond 5 and the smallest one gets passed back. We see a 9, which is beyond the search limit, and a 10, which is beyond the search limit. And we're keeping track of the smallest thing we've seen beyond the search limit, and so far the smallest thing we've seen beyond the search limit of 5 is a 7. We go over to the right hand side of the tree, we see a 5, we're still within the limit. We see a 19, we stop. A 12, we stop. And a 7, we stop. And the ultimate value of f that gets passed back is 7, because it's the smallest thing we've seen beyond the existing search limit of 5. And off it goes. So at each iteration it goes slightly further within the search tree. And because we've now incorporated this into a recursive algorithm that looks a bit more like a depth first search, we use less memory than we previously did in straight A-star search. So, this is nice. You can show that it's complete and optimal under the same conditions as A-star. It's often pretty good if your step costs are 1. It doesn't require you to maintain a sorted queue of nodes. It only requires a space that's proportional to the longest path, which is the really key quality that we're after here. And one finds that, in fact, the time it takes, unsurprisingly, depends on how fine-grained, if you like, how many values H can take. If H can take an awfully large number of values, then your F cost can also take a very large number of values. That might mean that you're just searching a very small amount further at each iteration. But if you're willing to make a little bit of a sacrifice in terms of optimality, then you can get around that. So one modification to this algorithm is actually to make it a bit simpler and simply increase the f limit that you're searching within by some fixed quantity epsilon at each step. And that means that you're not going to be optimal anymore, but you will be, at worst, epsilon away from the optimum f cost when you do find a goal. So there's possibly the first interesting engineering trade-off, if you like, within this course. This is really related to the fact that I've already pointed out that quite often in anything of interest in AI, we are dealing with things that are computationally very complex, and sometimes we need something suboptimal so that we can solve a problem within some reasonable amount of time. Well, here we're saying, let's drop the optimality, let's accept the fact that we might be a little bit worse than optimal, but in some cases the payoff is going to be that we can run faster because we don't expand our search out just by tiny amounts at each step and then keep regenerating the search tree. Recursive best first search is another way that we can try and use less memory, and in fact the idea here is just to use linear space. By doing a depth first search, in essence, we're doing something slightly different now to what we were doing with iterative deepening A star, because the idea is that we're going to do a depth first search and we're going to use f cost in order to guide it, so we're essentially still doing something very much like A star. But the trick now is that as we go down our search tree, we're going to use f to decide which node to expand next, but we're going to keep track at each point in the search tree of the best alternative that we've seen so far. So when we expand a state, we get some child states for it. We're going to go and explore the best one, but we're also going to keep track of how good the second best one is. Now, if at any point as we go down the search process, we find a state that's worse than one of the alternatives that we've seen on the way down, then we go back and explore the alternative instead. And the final thing is that as we rewind our search, we rewrite the f costs on the way back up so that we know how good a search tree might be if we go down it at a later time in the search process. This is the function that you need in order to achieve this. So once again, let me tell you what it does, and then once you know what it does, because it's recursive, it's much easier to understand what it does without having to really unpick a whole bunch of nested recursive calls. The idea here is that you call RBFS with a state that you've got to during the search and with an f limit, which is the best alternative that you've seen on the way to getting to S. Okay, now it returns either some S or a none, depending on whether you found a solution or not. If you return some S, then S is a goal and you're done. If you return none, then you haven't found a solution yet. Now, the return from this function is actually a pair, so it will, as its first element, have either some S or none, and as its second element, it will have the f cost that you got to after calling RBFS using some state S that went beyond the alternative in f limit. Okay, so it passes back two things: an indication of whether or not you found a goal, and if you didn't find a goal, the f cost that you did actually get to. Okay, and that's then used to rewrite f costs as you go back up the chain of recursive calls. So, if S is a goal, you're done. You return some S, and you don't really mind what else you return because that's finishing the whole process off. The next if just says that if there's nowhere else to explore, you're going to need to return and try an alternative, and at this point you would say that the f cost you've got to is infinite because you can't go any further. The for isn't strictly necessary, particularly if f is properly monotonic, I've simply introduced this here as an example of something I said earlier, which is that if f isn't monotonic, you could use the path-max equation to fix it. So this is just implementing the path-max equation. It just says if one of or more of the states S prime that you can get to in your next step actually has a reduced f cost, then use the older one instead. The while here is where the interesting stuff happens. Once again, we're just going to keep going around it and use returns to break us out. And it goes like this. You choose a new state, which is the best one that you can get to from S. Okay, so best here is an S prime which you can get to using an action from S, and which has the smallest f cost of the children that you can get to from S. Now, if the actual f cost of your best child is greater than the f limit, which is the best alternative f cost you've seen so far, then you want to stop the search, backtrack and try the alternative. So at this point you return none to indicate that the search is unsuccessful, and you return the f cost of the best child, and that's going to be used as you go back up the chain of recursions to rewrite the f costs of the parents so that you know how good that particular corresponding subtree within the search potentially is. Next best then is the child with the second smallest f cost. Now we want to know about next best because the alternative we see here to the best may be better than the one we saw further up the tree, which is represented by f limit. Okay, so we want to know what the potential next best thing here is, as well as what it might have been earlier on in the search. We then call RBFS recursively. We explore the best child, but we use an f limit which represents either the best alternative we saw earlier in the search or the best alternative we have here, whichever is the better. Hence we take the minimum of those two values. The return from this call to RBFS either says we have a solution or it gives us f prime. Now, f prime, when it's returned, is the f cost that we got to in the subtree we've just searched that went beyond the best alternative. So we rewrite the f cost of best using f prime. Okay, so as we come back up the stack of recursive calls, we rewrite f costs so that we essentially memorize how good the subtree might be. And finally, if the result that we got back actually was a result, then we return it and we're done. So here is an illustration of how it works. We start by calling RBFS on the root node again and using a limit of infinity because we haven't seen any alternatives yet. Initially, we're calling this on the root node. We look at its successors and we see that they have f costs of 7, 4 and 5. So, best, and the subscripts here are used to indicate which recursive call of RBFS they are local variables for. Best 1 now is the node with f cost 4. And next best has the value 5. And then we call again recursively using best 1 as the starting point. So we're going to do a recursive function call that's RBFS using best 1 as the starting state, 5 as the f limit because that's the best alternative we've seen so far, and it will return into a result variable and an f prime either as goal state or none for result 2, and and f prime, which will be used to rewrite the f cost of best 1 if we come back on the basis that we want to explore an alternative possibility. Okay, so the f cost of best 1 takes the return value f prime. We're now in the second call to RBFS, using best 1 as a starting point. Once again, we look at each of its children. We see they have f costs of 5, 9, and 10. So best 2 for the second recursive call, has the f cost 5, and next best is 9. At this point, next best 2 is a larger number than 5, which will have been passed to this function call as the f limit. And so, in continuing the search, because we haven't yet got to something that's worse than the best alternative, we will keep 5 as being the value of our best alternative. Now what's going to happen? Now we call RBFS for the third time, using best 2 as the starting point, and still with an f limit of 5, because that's the best alternative we've seen so far in getting to the point we are in the search. At this point, the children have values 11, 12, and 10. All of these are worse than 5, which is the best alternative that we've seen. So at this point, the recursive called RBFS returns none, because we found a point at which we want to cut off the search and go and look at the best alternative, and 10, which is the value of best 3, which we're going to rewrite the f costs with on the way up, because we want to memorize for the earlier nodes in the search how good it might be to actually follow them again. That means that the f cost for best 2 gets replaced by 10, and we keep rewinding the whole process. So we now have the f cost of best 2 replaced by the 10. Now once again, if we just look back slightly at that pseudocode, we're in a while loop, and what's happened is that within that while loop we've called RBFS, and it's come back, and f prime is 10, and f best has been set to f prime. Now the result was none, so we're going to go around the while loop again. So now we find best at the beginning of the while loop, but because we've rewritten the f cost of what was previously the best child, we now get a different best child. We also have to take account of the fact that the f limit here is local to this particular call of RBFS. So what happens when we look at the line if f best is bigger than f limit? Well, when we choose best now, what we actually get is the state that was previously the next best. It's the one that has value 9. The local value for the f limit is 5. Okay? So what we have then is the situation here, that best 2 has now been replaced and it's got a value of 9, whereas the local value for the f limit is 5, and that means that we're cutting things off and we're doing the return. Okay? Because here, in the while loop, under the first if, we now return none with f best, and f best is now 9. So we go back again, and we rewrite the value of the best node in the previous recursive call using the value 9, because once again we're keeping track of how good it might be to come down this part of the search process again. We're keeping track now of the fact that if we come to the second child of the root node, which initially had an f cost of 4, we've now replaced it with an f cost of 9, because we know that there's a subtree we can search under that state that will get us to an f cost of 9. Now we have a situation where essentially the entire process that I've just described repeats again. We've replaced the f cost by a 9. We're now back into the while loop in the original call to RBFS, but having replaced the f cost of the middle child of the root by a 9, we now have that the best node under the root has a value of 5 and the next best has a value of 7. And at this point we haven't gone beyond the original f limit of infinity, so now we go down into the right hand subtree and explore down there. So this one's a bit harder to get your head around, isn't it? You may have to think about this one for a while, but it's really pretty straightforward. All we're doing is going down what appears to be the best path in the tree. We keep track of the best alternative. If at some point it looks like the best alternative might be a better bet for us, we go back and we go and check out the best alternative. We just remember on the way back how good the initial search path was. So this is still nice because it's still optimal. It's now got a nice linear memory requirement. It's often found to be more efficient than iterative deepening A star. Its time complexity is hard to analyse, but it can be exponential. But the real problem that you can get with recursive best first search is that it can spend a lot of time regenerating nodes, essentially repeating its work. You may find that it goes down one part of the search, then goes and looks at an alternative, then comes back to the first part again, goes a bit further, goes back and looks at an alternative, and bounces between two or more specific areas within the search. Now that's all I'm really going to say for this course about better ways of doing this kind of intelligent search. There's a big literature on it. In particular, in some sense, these two versions that I've shown you, IDA star and RBFS, they try and limit memory too harshly. Okay. Essentially what we've tried with these two search processes is to try and get from a situation where maybe there's an exponential memory requirement down to one where it's just linear. And that's quite a big reduction. So you will find in the literature various other approaches, MA star, SMA star, which are memory limited A star, and simplified memory limited A star, which try and be a little bit more subtle. For example, you can try setting how much memory your search process is allowed to use, and then once that memory is filled, you have to find some way of deciding which bits of it to free up. Okay, but I'm not going to say more about that. Okay, it would probably be perfectly possible to give an entire 12 lecture course just on these kinds of intelligent search process, but there are lots of other things I want to talk about.